Hello students, welcome to our next physics class. So today we are going to continue with the next topic of the chapter superposition of waves. So in the last chapter we have studied about the displacement or the maximum displacement of a particle when two waves superimpose. So today we are going to go further than the topic, and today we are going to see two waves which are going to superimpose or superpose, but they are in opposite direction and they have the same amplitude. Then what are those types of waves called, and what are their theory, or what is their theory behind that? What are the equations of amplitudes? What is the equation of displacement? We are going to study all that. So let's begin. Now students, today we are going to study about a type of superposing waves or superposition of waves, and those are, which I'm going to tell you now. Please pay attention on this white screen. Okay. Now, imagine that there is a rigid support and there is this string which is in between them. Now, if I plug this string, there might be waves forming here. So this wave will go in somewhat this direction. It will get reflected and it will come back in this direction. Okay, students? So here one wave is moving in forward direction and one wave is moving in backward direction. So here two waves are superposing with each other. Now, this is what we get, or this is what is formed, is called as stationary wave or a standing wave. So students, imagine that when you plug the string, these waves are getting formed. Now, these waves do not move to the right or to the left. They are just stationary here. So we call them as standing waves or stationary waves. Now, students, in these waves, the particles vibrate about their mean position. So there are different particles at different positions and they keep vibrating. So these waves, since they are not a type of progressive wave, they do not progress ahead. The particles keep on moving with the same amplitude. Now here, some particles move with maximum amplitude and some particles move with minimum amplitude. For example, these points. Here, the particles move with maximum amplitude. And if you see these points, the particles move with minimum amplitude or maybe zero amplitude. The particle do not move at all. So students, these points of minimum amplitude or the zero amplitude are called as nodes of that waves, nodes. And these points which have maximum amplitude are called as antinodes, students. So nodes and antinodes is clear, I guess. So nodes are the positions of minimum amplitude or zero amplitude, and antinodes are the positions of maximum amplitude. Now we are going to see the derivation of, or the equation of, stationary wave on a stretched string. So if I have a stretched string like this, what is the equation of these stationary waves forming on these waves? On what is that expression? We are going to study that. So let's go ahead. Now students, we know that, or else you may consider, we have to consider two waves which are going in opposite directions. So we may consider this as the first wave. We may consider this as the second wave. So these are the two waves going in opposite directions. They have equal amplitude A. Students, just say both the waves have the same amplitude. That is, amplitude A is same for both the waves, and they are going in opposite directions, and their wavelength is lambda. Wavelength is also same. Both of their wavelengths is same. Now we need to recollect some few terms which we have studied in the past. Students, we know that 2 pi by lambda is known as k, and 2 pi by t is known as omega. And we know that 2 pi into 1 upon t, now 1 upon t is represented by n. So we can say that 2 pi n is equal to omega. So now we have to keep these two values in mind as we will require them in the further derivation. So let's go ahead now. Now students, what are the equations of these waves? The equation of wave traveling in along the positive x direction. So students, if the wave is going in the positive x direction, what is the equation of the wave? How do we write that equation? We have studied it. So let us say it is y1 of the first wave. So it will be a sine 2 pi n t minus x upon lambda. Is it clear, students? Yes. And what is the equation of a wave which is going in negative x direction? So this was going in the positive x direction. If a wave is going in negative x direction, what will be its equation? We will say it will be y2. So it will be a sine 2 pi nt plus x upon lambda. So this will be the equation of wave which is traveling in negative x direction. Okay. Now students, by principle of superposition of waves, what will be the resultant displacement of the particle? So by principle of superposition of wave, we will get y is equal to y1 plus y2, the maximum displacement of the two waves. So what will it be? So just add these two equations. So what we will get, y is equal to, we will substitute the value of y1 and y2. So y1 is equal to a sine 2 pi nt minus x upon lambda, and plus y2 is a sine 2 pi nt plus x upon lambda. So these are the substitution of values. Now students, how we will solve this further? Now we know a formula of a trigonometric result, maybe, that is sine c plus sine d is equal to, what is the formula students? 2 sine c plus d upon 2 cos c minus d upon 2. So these are the two, this is the formula of sine a plus b or sine c plus d. So now we have this similar formula here, sine, this is the sine c part and this is the sine d part. So let us solve this further. Now we will take this a common outside because it is there in both the terms and it is not required in the formula. So I'll just take that out and let's see how we can apply the formula. So I'm applying it on the next screen, pay attention. So what will I get students? Y is equal to 2 and that common a will be outside, sine c plus d. So sine, what is c, value of c? 2 pi nt minus x upon lambda plus d. What is the value of d students? 2 pi, or else let me remove that bracket, 2 pi nt plus x upon lambda. So this is the value of c plus d whole upon 2 into cos of c minus d upon 2. So what will be c minus d upon 2? 2 pi nt minus x upon lambda c minus, what is the value of d? 2 pi nt plus x upon lambda, and whole thing divided by 2. So this is what we get. Now let's solve it further. So what will I get? Y is equal to 2a. Now let me solve it further. Sine of 2 pi nt, I will just multiply it inside, minus 2 pi x upon lambda plus 2 pi nt plus 2 pi x upon lambda, whole thing upon 2. What will be the value of cos here? Just pay attention. This was the value of sine. Now cos 2 pi nt minus 2 pi x upon lambda and minus 2 pi nt minus 2 pi x upon lambda. So that minus sign will be considered here upon 2. Now which are the similar terms which are getting cancelled out? Here this term is getting cancelled out. Here this term is getting cancelled out. So let's see what we are getting further. Y is equal to 2a. Here sine, students, 2 pi nt plus 2 pi nt, we will get 4 pi nt upon 2. And for cos, what we will get? Minus 2 pi by 2 pi x upon lambda minus 2 pi x upon lambda. It will be minus of pi x upon lambda upon 2. So this is what we get in cos. Now y is equal to 2a. What will be the further step? 2 1s are 2 2s are 4. So sine 2 pi nt into, students, cos of minus theta is cos theta. We know that. So we will write it as cos of 4 pi. Here also we can cancel out. 2 1s are 2 2s are. So I'll just write it again. Cos 2 pi x upon lambda. So this is what we get. Now students, pay attention carefully how I'm making the arrangement. So I will write the cos term before. So 2a cos 2 pi x upon lambda into sine 2 pi nt. So I'm writing it in this manner. Now students, this whole term, we consider it as amplitude of the wave. So I'm writing it here. So let 2a cos 2 pi x upon lambda is equal to capital A. That is the resultant amplitude of the wave. So what we will get, what will be a final equation? Y is equal to A sine 2 pi nt. Now students, can you see this term 2 pi nt? So what is the value of 2 pi n? We saw at the start, it is omega. So we can substitute that with omega. So A sine omega t. So this is the final equation which we get of a stationary wave, that is sine A sine omega t. So this is the value of a stationary wave or a standing wave. The resultant displacement, and A is the maximum amplitude of that wave. Now let's go ahead, students. So this was the equation of that wave which we derived. Now there will be a condition for node and antinode. So before that, we will study what is actually a stationary wave, the definition of a stationary wave. So students, all the particles of the progressive wave all the particles of this stationary wave of the string pass through their mean position simultaneously, twice. That is once during each vibration. The string as a whole is vibrating with frequency omega, with different amplitudes at different points. So each point has a different amplitude. So for example, this point is vibrating with this much amplitude, this is vibrating with so and so amplitude. So students, each point has different amplitude, and so on. The particles have different amplitudes here, and the wave has the same frequency which is going on here, the vibrating frequency. So thus the wave is a standing wave. So let's see what is the definition of a standing wave. Okay, so here is the definition of a standing wave, students. So when two identical waves traveling along the same path in opposite directions interfere with each other. So students, two identical waves, that is they have the same amplitude, same frequency, but direction is opposite, traveling along the same path but in opposite directions, interfere with each other. Resultant wave is called a stationary wave. So this is the definition of stationary wave. Now students, we will see the conditions for nodes and antinodes. So let's go ahead. Now let's see what is the condition for node. Now students, tell me, what is a node? Now when a stationary wave is passing like this, wait a minute. Okay, so the points of minimum displacement is called as node. So let's see the condition for nodes. So students, we know that at nodes amplitude is 0 or minimum amplitude. So we can say that at nodes amplitude is minimum, right? So we can say that amplitude is 0 almost. So the particles don't vibrate at all at nodes. So we can say the amplitude is 0. Now students, what is the formula of amplitude which we considered? A is equal to 2a cos 2 pi x upon lambda. So this was the formula which we considered for amplitude. So we will take this value as 0. So it will be 2a cos 2 pi x upon lambda is equal to 0. Now let's see, now this 2a term will go on that side. What we will get? 2 pi x upon lambda is equal to 0. Now if I take 2 pi x upon lambda is equal to cos inverse of 0. Now students, when is the value of cos 0? So it is at 90 degree. Yes. So students, that is pi by 2. So we can say that we get 2 pi x upon lambda. Students, this is lambda is equal to, we can say at pi by 2. Pi by 2 we get this value. Similarly, at which positions it will be pi by 2 again at 3 pi by 2, again at 5 pi by 2, and so on. So in similar way, we will get it accordingly. Now students, if I solve this for the first antinode, first node, 2 pi x upon lambda is equal to pi by 2, what will I get? So pi will get cancelled out. X is equal to what I get, students? what will be the value of x which I'm getting here? Lambda is going there, 2 is getting multiplied with 2. So I'm getting lambda by 4. So lambda by 4 is the value of x, that is the value of displacement. And similarly, I will get it as 3 lambda by 4, 5 lambda by 4, and so on. So students, we can say that we can generalize the formula for x. X is equal to 2p minus 1 lambda by 4. So where p is 1, 1, 2, 3, and so on. Okay, students. So in similar way, we can find out the positions of the nodes for this particular wave. So what is the condition for nodes, students? Nodes occur at the values of lambda by 4, 3 lambda by 4, and 5 lambda by 4. So in a wave, nodes will appear at these positions and at degrees of pi by 2, 3 pi by 2, 5 pi by 2. Okay. Now let us see what is the condition of antinode. So let's go ahead. Condition for antinode. Okay. Now students, tell me what is the position of antinode in a stationary wave. So if I have this stationary wave here, so the position of maximum amplitude, the maximum amplitude here is called as antinode. So at antinode, we can say amplitude is maximum. So we can say at antinode, amplitude is maximum. Okay. So now what will be the amplitude, maximum amplitude? Each wave has an amplitude A. So we can say the amplitude will be 2A, because if this wave we consider and this wave we consider, so it will be A and A, which we will be getting as 2A. So we will consider it as 2A. So for example, we will say amplitude is equal to 2A. And this plus or minus is taken as, since it is from upper position and lower position, we take it as plus or minus A here. So now students, let's see. A we have as 2A cos 2 pi x by lambda is equal to plus or minus 2A. Now, if I cancel this out here, what I get? Cos 2 pi x upon lambda is equal to plus or minus 1. So I will get 2 pi x upon lambda is equal to cos inverse of plus minus 1. So when is the value of cos? 1. Yes, students, when is the value 1? Yes, at 0 degree. So we will get 2 pi x upon lambda is equal to 0. Also, when we get cos value as 1, it is at 180, then so on, 360 and so on. So 2 pi, 3 pi, dot, dot, dot. Now students, if we solve for first value, what we will get for the condition of antinode? So if we solve this, 2 pi x upon lambda is equal to 0. So what we will get? X is equal to 0. Then for second one, if we solve, students, 2 pi x upon lambda is equal to pi, what we will get? We will cancel out this 2, x will be lambda by 2. So at lambda by 2 position, there will be a antinode. So what will be the values of x? 0. Then we will get lambda by 2. Here we will get it as lambda by 2. Further, we will get it as lambda. Then again at lambda by 3 lambda by 2, and so on. So similarly, we will get nodes at these particular positions. Now students, what can we say about the position of node and antinode? So students, nodes and antinodes, two successive antinodes or two successive nodes have a difference of pi by 2, students. So they occur after a difference of pi by 2, and a node and an antinode occur at a distance of pi by 4. So this is what we have to keep in mind. Now students, we studied this about a transverse wave. We saw this about a transverse wave. But what about a sound wave which is longitudinal? So if you consider this air column here and we consider a sound wave going inside it. So usually we represent it with a transverse wave, but in actual, it is a longitudinal wave. So in longitudinal wave, those vibrations, the compressions and rarefactions are traveling, and stationary wave is being produced in that pipe. So that is about sound waves which are traveling, longitudinal sound waves. So students, that was it for our today's lesson. So today we studied about the equation of stationary wave on a stretched string. So we derived an expression for the equation of that wave, stationary wave on a stretched string. Also, we saw the two conditions for nodes and antinodes, and we saw the definition of a stationary wave. Now in further topic, we will study about the properties of stationary waves. So students, that's it for today. Thank you so much. See you next time.